As a concluding discussion of research method, we will talk about inferential statistics in more detail. Inferential statistics different from descriptive statistics. Descriptive statistics simply describe data. On the other hand, in inferential statistics, you try to penetrate the data to understand the nature of the trend. And that the reasoning is based on two elements, which we will talk about in the next few slides. Number one, we have an assumption that the observation is the truth plus error. So that's number one. Number two is there are certain relations between observation and underlying truth, which is a probabilistic. And both of these things are discussed in the subsequent slide.
So in the previous slide, we talked about inferential statistics and how it works in a very general way. So the one of the most difficult things that students usually experience about inferential statistics is the meaning of the population and how it's different from sample. So here in this slide, that's what we want to talk about. Many textbook or the lecture-based discussion typically says a population is any entire collection of peoples, animals, plants, or things from which we may collect data. It's the entire group we are interested in and which we wish to describe or draw conclusions about. So this is the standard description, but still this is very abstract. So okay. So the best way for you to understand the population is the population is abstract truth, which is categorically described. So this issue of population arises from our psychology, how our thinking works. Our thinking and communication system is categorical, such as that when we talk about our weight, I say my weight is 150 as opposed to 150.1123565523 in some continuous way. So we describe anything in the world pretty much categorically. So therefore we are simplifying it, whereas the actual thing is that's not that simple, and it's probably ever changing. My weight is changing minutes by seconds, and so it's impossible to actually categorically describe my weight. But nonetheless, our communication needs gives that we need to describe it in categorical ways, such as it's 150. Therefore, the population is actually should be understood as model or simplified categorically described truth, which kind of is based on a large sets of data. Okay, so it's an abstraction. And number one, we use parameters to describe population, such as mean and standard deviation. So when I say my weight is 150, that is an informal population mean because this number is based on my implicit averaging of infinite number of implicit observation. Okay, and on the other hand, and then the other things that is then how this is related to sample. On the other hand, the sample statistics is actually located in a particular space and time, whereas the population is not. So the sample statistic is actually observable, okay, because it's situated in a particular time and space. But the sample statistics of mean actually deviates from population parameter because observation is always situated in a particular space and time, and the population is the abstraction. So therefore that's the difference. Okay, number three that you need to understand, because of this kind of complexity, population needs to be defined before you collect the data. So we will talk about these things in the next one. Okay, next slide. And then what you really need to understand is in your research, your conclusion is always about the population. Nobody is really interested in the sample itself. Sample is important to the extent it helps you to infer about the general trend, which can be categorically described as a simplified truth. So therefore, your conclusion is always about the population. Okay, and the nature of your population that you are interested in, therefore, determines how you collect your data. So in this slide, we would like to practice our thinking about how population and a sample are related. Okay, so let's look at these three different kinds of research situations. Uh, the first one, you are interested in knowing whether exercising, such as 2 miles a day running, is reducing your weight. In this case, what you are interested in is your weight. So therefore, your population is about you. The only extension is the time. So therefore, your sample should extend across the time dimension. And it doesn't extend to multiple people. Okay. In number two, you are interested in knowing whether exercise reduces weight among college students. In this case, your population, that's what you're interested in, is not just you but among college students. Therefore, you are interested in is what you're interested in is not about the time, but whether or not this question of running 2 miles a day reduces the weight in general among people. So therefore, what you need to collect the data is the representative sample of students. Contrast this with the question, the issue number one. In the number one case, your representative sample should be about the time, not about the people, because you are interested in only your weight. Okay. In the number three, now you are interested in knowing whether running 2 miles a day along different types of courses, such as uphill, downhill, or flat course, affects your weight. Okay. So in this case, it's the the question that you are interested in is still you. Okay, but more interesting things that are according to what your research question that you want to generalize is 2 miles a day, whatever the different kinds of courses are. So you are not kind of that becomes the random one. So therefore, your sampling strategy should focus on different types of courses, not time, not a person. Okay, so see that 1, 2, 3 is pretty much the same question, but the population that you are interested in are different. In number one, it's you, but the generalization across the time. In number two, it's the students, general college students, and then number three, it's across the different types of courses on which that you run 2 miles a day. Okay. So I hope by the discussion on the previous slide, I hope you at some intuitive level understand why different types of sampling strategies are needed in order for the questions on different kinds of population, namely time, a person, or different kinds of courses or items. Okay, so now in this particular slide, I try to kind of discuss and explain why, in kind of mathematical, more technical sense, different kinds of those different kinds of strategies are needed to accomplish these different kinds of research. Okay, So the reason why different population require different kinds of sample is based on this notion that sample statistics equal population parameters plus error. So the sampling, which is actually the observation, contains some sort of errors. And in order to get to the actual population parameter, which can only be estimated, that means you have to estimate the error. So that means in order to get to the population parameter, you have to subtract the error from the observation, actual observation. So then, how you are going to estimate the random sampling error? Okay, in random sampling error, in estimating the random sampling error, I assume that in your stats lecture you learned this formula. Random sampling error, which is a standard, kind of represented as a standard error of the mean, can be given by standard deviation divided by square root of sample size. Okay, and given that we don't have a population standard deviation, therefore what we're going to get is we are going to substitute sample based standard deviation divided by square root of n. So here what you need is the sample standard deviation. Okay, so given the standard error of the mean is estimated by sample standard deviation divided by square root of n, therefore we need standard deviation, and this standard deviation of the sample needs to extend to respective population dimension that you are interested in. So in that case, if you are interested in your weight across different times, then your sample should be across different times, which becomes your sample size. Therefore, that becomes the square root of n. For example, if you have 30 times of observation of your weight, then whatever your standard deviation of your weight across those sample needs to be divided by 30 square root of 30. On the other hand, if your question is about the weight of the college students, then you get the sample, representative sample of say 100 people. Then the standard deviation across those 100 people's weight needs to be divided by square root of 100. And finally, if your research question is about running different types of courses, then your sample are running many different kinds of courses and then weighing your weight. Then in that case, whatever the variation in the courses included in the sample, say that you're running 10 different kinds of courses, and then a standard deviation of the weight across running these 10 different kinds of courses should be in the numerator, and it needs to be divided by square root of 10. Okay, so this way you are actually thinking about different dimensions, which you see in the next slide. So this slide is kind of trying to capture what we discussed so far, which is the fact that population has multiple dimensions. I can think of 3 right now. Population can extend the generalization across time, which is like the example of your weight across different times. In that case, your sample should extend on time, like your weight measured in the morning, daytime, and so on. So 20 times a day, 30 times a day, that's your sample. Or a population can extend across people. In that case, the generalization is across people. Say that you are interested in UA students' weight, then your sample should be representative sample of UA students. Okay. Then finally, it can be across items, such as our example is running different types of courses. In that case, it generalizes across the same 2 miles a day, but generalize across many different kinds of courses. whether it's uphill, downhill, flat courses, so on and so. So in that case, your sample should extend across different types of items, such as different types of courses of running. Okay, and unfortunately, research cannot simultaneously address all these 3 or 4 different kinds of dimensions of population. Therefore, you selectively deal with each of these different kinds of dimensions. These are called, as discussed in the previous sample, it's called random factors. Random factors means basically in case that you are sampling that are randomly different types of times in weighing your weight, then the random factor is a time. If basically you are randomly sampling the people, your random factor is a people. And then if you are randomly sampling different types of courses, then your random factor is the course, which is an item. Okay.
It's a second element of the reasoning, which is inductive logic of hypothesis testing. So the elements of hypothesis testing in statistics is now you have a prior belief, which is a null hypothesis. That's default. Two means assumed to be the same because there is nothing else that you know. Okay, that's basically the beginning of your reasoning process. And then you have a decision process threshold, which is indicated by the probability value and alpha. So this is basically the area that separates unlikely from likely. So this means given your prior belief, certain kinds of things should not occur. So that's the alpha level. And then there is a degrees of freedom. Degrees of freedom is the property of your sample size. The larger the degrees of freedom, you have more trust in the accuracy of the data. Okay, and then finally, based on these, you're going to compute observed sample statistic. So here we did talk about the detail of logic of hypothesis testing. So like explained in the previous slide, you begin the process by assuming that the null hypothesis is true. The reason why is you don't know anything else. So you just have to assume that null is true. Okay? So two means are the same. That's your initial assumption. And then you set up the alpha level. The alpha level is the borderline that divides the likely from unlikely. So likely is given or assuming that null is true, which is two means are the same. What's the likelihood a particular kinds of sample statistic is likely to happen if the null is true? Okay, so that's the alpha level. So this means if the alpha level is low, like 0.01, you are setting up the very extreme area so that if the null is true, this kind of extreme value should not happen. And then you're going to compute observed statistic. Observed statistic in the t-test is the difference between two sample mean divided by standard error of the mean. If you're computing the 3 or more sets of interval scale data, use f-test, f-value, and so on and so. And then you're going to compare the observed value and the critical value, which is based on the alpha. So the logic goes like this. Given that we can actually figure this out, the likelihood of a particular t-value given the degrees of freedom based on the normal distribution. That means if you have a particular t-value, the likelihood of t-value under the normal distribution can be computed. That's the t-table, t-distribution. And then you have an expectation that if the null is true, that kind of t-value should not happen. Then if extreme t-value associated with extreme low levels of probability happens, then you need to start believing that your original hypothesis, which is a null hypothesis, is not true anymore. And that is the basic gist of uh, logic of hypothesis testing. So you try to challenge yourself, and then you are hoping that the new data is going to force you to change your belief. So there are three different kinds of inferential study techniques available in statistics. Number one is non-parametric hypothesis testing, which is like chi-square. This is used when you have a categorical variables and your variable is not interval scale. Number two is analyzing the relationship between variables, which is the correlation, partial correlation, multiple regression, this kind. And then finally, parametric hypothesis testing, when your central tendency is expressed with the mean, which is, for example, when your measurement scale is interval ratio. In that case, your parametric hypothesis testing uses t-test, one-way ANOVA, or two-way ANOVA, or analysis of covariance. Then an example of hypothesis testing, non-parametric hypothesis testing with chi-square. So the chi-square works when your variable is categorical. So in this case, you have 2 by 2 chi-square, where two variables are smoker versus non-smoker, and then fewer than 3 times a week exercise, or at least 3 times a week exercise. So you can see 12 people are smoker who exercise fewer than 3 times a week. Smoker who at least 3 times a week exercises 6 people, and non-smoker who exercise fewer than 3 times a week is 9. Non-smoker who exercise at least 3 times a week is 19. So the test that you are interested in is whether or not status of smoker or non-smoker is somewhat systematically related to whether or not you are exercise fewer than 3 times a week or more than 3 times a week. The first step in computing a two-way chi-square is to compute expected frequency. So rather than me explaining this, you should look at the example, the description that's written here. But the key idea here is you get to do expected frequency. You have to compute the expected frequency for these four cells, like smoker exercising fewer than 3 times a week, smoker exercising at least 3 times a week, non-smoker exercising fewer than 3 times a week, and non-smoker exercising more than 3 times a week. Okay, so let's look at the first one, smoker who exercise fewer than 3 times a week. The number of smoker is 18 out of 46. The number of people who exercise fewer than 3 times a week is 21 out of 46. So when you multiply 18 by 21 divided by 46, this is going to give the number expected frequency of smoker who exercise fewer than 3 times a week. And you repeat that 4 times to get each of these estimates, such as 88.2, 12.8, 9.8, and 15.2. The second and the final step of computing chi-square, for each cell, you are going to compute the difference between observed frequency and expected frequency, and then you're going to square, and then you divide the square of the difference by the expected frequency. So the chi-square for the first cell, which is a smoker who exercises fewer than 3 times a week, is 1.8. And then you computed each of these four cells, and then you sum them up. And that's 5.4. And the p-value corresponding to 5.4 with the degrees of freedom 1, because it's a 2 by 2, 2 minus 1 multiplying 2 minus 1, the degrees of freedom is 1, then its a p-value is 0.021. Therefore, you can reject the null hypothesis. This means smoker, non-smoker status is systematically related to the number of exercising, whether 3 times a week or more than 3 times a week or fewer than 3 times a week. Now we are moving on to correlation. So in order to analyze using correlation, you have to have a paired observation for each person. So as you can see, in this case, two variables are measured, number of class missed and then exam scores. And then so you can see that when you actually have two scores or measurement scale measure associated with each individual, you can find the coordinate or the relation between that by plotting on the scatter plot here. Examples of the scatter plot of perfect positive, perfect negative, and curvilinear correlations. Curvilinear correlation cannot be analyzed with a correlation because the negative part and the positive part cancels out. As you can see, according to the scatter, there seems to be correlation. The first part is positive, the second part is negative. When you actually compute the correlation, correlation is going to be nearly zero because of cancellation between the positive and negative. So here are three examples of correlation. All of them are positive. The first one is 0.32, and second one is 0.53, and the last one is 0.8. As you can see, as the scatter gets narrower and more clearly defined, the correlation gets higher. Now, everybody should be aware that correlation should not allow you to conclude the causal relations. Okay, so two issues unaddressed in correlational studies to conclude some kind of causal relation is lack of control in temporal precedence. A is causing B or B is causing A, even if they are correlated. And also, A and B correlated doesn't mean that A is causing B or B is causing A, because it could be C is causing the variability, that the correlation in both A and B, between A and B. In actual analysis of correlation, it's typical that even if you are interested in correlation between variable A and B, you also measure other variables, and as a result, you create or describe the overall patterns of correlation by creating correlation matrix like this. So you should get used to looking at this type of correlation matrix. So in looking at the correlation matrix, I would like you to become capable or competent inferring the actual relations that's depicted in correlation matrix. So in this case, exercise and anxiety is correlated by negative 0.6. And anxiety and income is negatively correlated. But exercise and income is perfectly correlated. So by actually creating this diagram at the bottom, you have an easier time understanding the overall relation between the three variables. So furthermore, what's important here is even though exercise and anxieties are correlated at negative 0.6, that correlation may be entirely due to anxiety and income level, because exercise and income is perfectly correlated. So if you can draw this kind of diagram, it helps you to really discern, figure out the overall, based on the overall pattern of correlation, uh, how anxiety, variability in anxiety can be explained by exercise and also by income. Okay, so here a proportion of anxiety explained by the variability in exercise is 36%, because R squared equal 0.6 multiplying 0.6. Proportion of anxiety explained by the variability in income is also 36%. Okay, so now what about the proportion of anxiety explained by the exercise through its relation to income level? Okay, so that's 100% of 36%. So therefore 36%. So this means if you remove the proportion of anxiety that's explained by the exercise through income, which is 36%. And if you remove 36% from 36%, exercise doesn't explain any variability in anxiety when you remove exercise's influence of anxiety through income. So there is no real direct effect of exercise according to this pattern of correlation. So the operation I demonstrated in the previous slide through diagram is a kind of informal analysis. The more formal analysis of the similar operation in using SPSS or other kinds of statistical package or software is actually, there are two different kinds that you can select. One is a partial correlation. So in the partial correlation, you analyze the strength and direction of target relationship after partialing out. That means separating or controlling the contribution of the third variable. Also, multiple regression, there are different kinds of multiple regression available, and you can simultaneously analyze the contribution of different kinds of predictor variable.
So you don't have to worry about the exam. So the reason why we are doing this is because in case that you in the future you use multiple regression, at least you have an idea of what you need to pay attention to. So these red values are the one that you need to pay attention to. So the first one here, the number one model is for example, you try to predict the level of happiness from love, income, and exercise as a predictors. The first model that you enter only love. So the love is predicting the happiness in the number one model. I'm looking at now the second table. The beta is negative 0.088, so it's not that much. Okay, and then therefore it's not significant. Like t value is it's not significant. Okay, and look, significant change is 0.50, so that means overall model is not significant. If you know, but now let's think about now. So it's a second model. You enter income and love. So in addition to love, you enter income. Okay. So in this case, the R square is 0.048. Okay. So that means now the model total, when you look at the love and income together, approximately 5% of the variability of the happiness is explained by the love and income together.
Right.
Okay. So the R square change is 0.41 because it's the change from 0.007 to 0.48. So it's about a 4% change. Okay. And now F change is significant. It's getting small, close to significant, but it's not really significant because it's 0.09. That's the significance level. Finally, if you enter everything, an exercise together in this model, now the R square goes up to 32%. Okay, so this means the R square change is 27% beyond the second model of love and income together. This is significant because now significant F change is 0.000.
Right.
Now you can interpret the beta, which is down here. It's 0.587.
Right.
And then standardized coefficient is 537. So this is about basically 0.5 partial correlation. That's what it means. So the final model is significant. That means only thing that's significant predicting the happiness in this particular data set is an exercise.
All right.
That's how you look at it.
So does the low level of 0.59-ish on the final model, does that indicate that there are other third variables that account for the other 30 or 40% or so?
No, so no, that's right. So that's an error. So that means, okay, so the total is if the model is perfect, the 100% should be predicted, right? But it's overall what's predicting is only 32.3%.
Okay.
So that means it's actually 68% is error.
Okay.
It's not predicted.
Alright,
Okay.
so the beta then.
Yeah, it's not the beta that you pay attention to. What is the overall percentage that's predicted? In order to look at it, you have to look at R squared.
Okay.
That's 82%. The coefficient beta is basically you treat it as the same as almost like a correlation.
Alright.
Okay?
Okay.
So this alone is only correlation is about 0.537, but the overall model explains about 32% of the variability of the happiness.
Okay.
That's how you interpret it. That means about still 68% is not predicted at all. You don't know what's going on about that part.
Okay.
That's an error. I think so. This is kind of difficult to right now. I think it's kind of difficult, but as long once you start using that, you're gonna get used to it. My whole point is to just expose you. I don't expect that you understand everything in here, but I want you to at least get an idea about what you need to pay attention to. Those are R square and F value and beta. Those are the three values that you pay attention to in interpreting multiple regressions. It's going to take a while for you to get used to interpreting the meaning of this, the output.
Right.